Hey, good afternoon, everybody. Dr. Daniel Barth here with you with the 60th episode of How Do You Know? I'm kind of stunned by that. And we see an image here coming up of the Star Mentor book. I hope you have, if you're a telescope owner, if you're a binocular owner, if you've been working, I hope you have taken a look and ordered your copy of Star Mentor. Star Mentor, basically a distillation of 45 years in the classroom teaching other people introductory astronomy with small telescopes and binoculars. You want to know what to do next. How do I learn the sky? How do I understand what I'm seeing at the eyepiece? This is your guide with a step by step set of activities with instructions, drawings, sketches, pictures, everything you need to help you. It's, as one of my reviewers said, like having a conversation with an old friend, which really, I found that flattering. And if you're a fan of this show, I hope when you read the book, you will kind of hear my voice in your head as you read as you read the various activities. It's my way of being with you at the eyepiece when you're out in the dark enjoying the night skies. And if you've already got your copy of the book, I do hope you'll take some time and post a review on Amazon or whatever other website where you purchased it, or even on your Facebook page, because those sorts of things really help. We want to take just a moment this afternoon, and I have questions every once in a while. Gee, Dr. Barth, what do you do? What do you doctor of? And what do you do at work? And essentially, my doctorate is in STEM education. And what I do now is I train young teachers to teach astronomy and space science. I run the Astronomy for Educators program at the University of Arkansas Fayetteville campus. And the Astronomy for Educators book, now about 8,300 teachers in more than 60 countries use this book. It serves more than 400,000 people a year. You can download that one for free. So if you're interested in astronomy education, you can put Astronomy for Educators into almost any search engine and you'll find the download for free. And I want to show you one of the things. Well, what do you do at work? So I'm going to show you. This is lovely. This is one of the things that I do at work. This is called the Star Lab Planetarium. And the lovely thing about this machine, this is a 1990 vintage inflatable planetarium. That tube you see off to the right is actually the entrance and exit tunnel. This dome is 24 or 5 feet wide, about 18 foot tall, and you see there it's in a school gymnasium, and it takes up about half of a basketball court. It's an absolutely enormous thing. The projector is truly old school. The projector runs off a single tiny incandescent bulb, and there are masks that you put on, and they rotate. You can show constellations, you can do galaxies, you can do plate tectonics, ocean currents, all sorts of crazy stuff. But it's really a fantastic instrument. We take this out to about 20 or more shows a year, where local schools within about 60 or 70 miles of Northwest Arkansas, they contact me and they said, "Oh, hey, Doc, can you come and do a planetarium show for us?" We schedule a time. The school actually transports the materials, and then I show up and set everything up. And we run shows for the kids. We can put about 25 people inside. And this is one of the most popular things I do at work. And people just love it. So we're going to go ahead and turn that off, and we'll go back to our regular screen. There we are. And as we have usually been doing, we have our book of the week. And here's our book of the week this week. This is called Red Rover, the inside story of robotic space exploration from Genesis to the Mars Curiosity rover. And this is a really fascinating and very readable book. This is one of the basic books group, and this one by Roger Vines, Wines. So if you go looking for this at your local library or at wherever quality books are sold, this is a really lovely book if you're interested in space exploration and science. Okay, so let's go ahead and get into the heart of our talk today. I sat down this week and I said, "Ooh, what am I going to do?" And it's for me, this is one of the best parts, picking a new topic to talk about each week. And there was an article. Oh golly, Einstein's theory of relativity has survived another test. And I said, "Ooh, I'm going to do a program on testing the theory of relativity. Can you prove Einstein right? All these things." And as soon as I got into it, I realized, you know what? I'm going to have to back up. I'm really putting the cart before the horse because in popular science literature, I see things like proving Einstein right. You hear things in the popular media. You can't prove that. Where's the proof? And in fact, this isn't something that scientists say, not legitimate scientists anyway. So I thought we would go ahead and take a minute and show today and talk about how do we understand facts, hypotheses, theories, proof, evidence, and sort of lay this all out for you. And then next week, we'll jump into testing Einstein and how we do that. You hear the "you can't prove that" on social media all the time. I have seen this stuff. I follow the James Webb Facebook page, the James Webb's telescope, and people from NASA and Webb has a voice. Oh, I'm looking at this now. The rovers, they do this with the rovers as well, and it's quite delightful. And you see in the comments, well, they can't prove that. There was a story about cosmic microwave background in the Big Bang. And somebody, oh, nobody's proven the Big Bang is true. Well, let's back up and examine these. We have this feeling in our hearts when somebody says, you can't prove the Big Bang really happened. We have our feelings in our hearts as interested, scientifically literate citizens that there's something wrong with this kind of an outrageous claim. But how do we counter it? If we say, oh, I'm a fan of the Webb telescope, I love Hubble, haven't you seen some of the, or you can, and you run into people in real life and online who are just like, oh no, that's not true, you can't prove that. And so, how do we answer these people? So let's take a look and define some terms, shall we? Let's start out with facts. Facts, my friends, can be established by measurements or observation. And if you're a scientist, usually both of those things. And these measurements can and should be repeatable by any interested party. That's what makes it science and not opinion. You can say things like, the sky is blue. The mineral has a Rockwell hardness of 7.2. The wavelength of this laser is 580 nanometers. And it may be printed on a sticker on the end of your laser pointer, but you have confidence that you could take this laser pointer to a laboratory and you could say to a scientist, please measure the frequency and the wavelength for me. And that a scientist could do that and you could verify the claim on the sticker. It's like the manufacturer says, your car has 250 horsepower. There's some assumption there that the manufacturer is telling the truth within limits, and you could take your car to a test facility and test the horsepower on a dynamometer, and you would come up with a value that was similar to what the manufacturer said. Facts can be shown to be indisputably true. However, facts cannot be refined to an arbitrary level of accuracy. Give you an example. Let's say I take something really simple. I have here a ball of modeling clay. And I have a ball of modeling clay, and I say, oh, this is 50 grams of modeling clay. And someone says, no, it's not. I have a balance, and I'm going to show that this is 50.00275, and you're off by 00275. And I say, oh, well, that's nice. My scale only goes to 50.0. So who's right? This is, in fact, a 50-gram ball of clay. Okay. But we cannot have an arbitrary level of accuracy. We cannot say, oh, I want to measure that clay to 50 decimal places. There's no scale on the planet that will do that, no matter what units you're measuring in. So facts can shown to be indisputably true, but an arbitrary level of accuracy just isn't possible, because accuracy is about our tools, and the statement about the mass of a ball of clay is about the ball of clay. And those things are different. Facts can be shared by everyone. Observations, if they're legitimate scientific observations, can be repeated by any interested party with the right equipment. Anybody with a kitchen ingredient scale, I could ship you my ball of clay in a Jiffy Pack mailer, and you could put it on your kitchen scale and verify this is 50 grams of clay. No, we're not going to do that. But the idea that someone could say, oh, I've caught the largest catfish in the world. I've measured the bond angle of a water molecule. These things are things that can be repeated in different laboratories, from someone's kitchen to a high school laboratory, university, or a very specialized technical institute. Measurements, as I've said, measurements have an accuracy limit. If I say, oh, here's a tape measure, and I'm deliberately not showing oh, it's upside down in our view, isn't it here? There we go. That's a little better. I'm not showing the brand name of the tape measure. It's not necessary. And you can see that this is definitely an American product because it's measuring in inches. Oh, well. But this thing has an accuracy, and this tape measure goes down to about a 32nd of an inch. Can you measure to a hundredth of an inch, a thousandth of an inch, a millionth of a meter, or whatever? Yes, you can, but not with this device. Every device has its own limits. And as scientists, we have to understand, how good is our tool? Whether we're measuring mass, distance, velocity, wavelength of light, how good is our tool? And when we state a number about a fact of length, mass, height, hardness, whatever we're measuring, we have to be honest about what our tool allows us to do. On the other hand, electronic calculators are quite notorious because they will give you answers out to as many decimal places as you wish. And a lot of times those become a fantasy of the mathematician, because in fact, although the calculator might say the ratio between two numbers is infinitely long and it's an irrational number, well, surprise, if it's a ratio of two measurements, the tools used to measure those things are not infinitely precise. So what happens when scientists attack? And Paul put that little catchphrase up, and I got that off a screwy program on YouTube, when sharks attack, when bees attack. It was some crazy thing. And I said, okay, well, what happens when scientists attack? Scientists generally, and they do attack each other. We've talked before many times about Karl Popper, and I outrageously oversimplify his work by saying Professor Popper says that science as a community activity is kind of like a cage match, last fighters standing. But in fact, it's true. Scientists do attack each other's measurements, their procedures, their theories, their ideas, and they generally attack along two different lines. The first one is to say, oh yes, well, guess what? You didn't measure that correctly. And this boils down to a couple of possible things. One, they might be saying, I think you were fooled. I think you didn't measure it correctly, or you didn't measure what you thought you were measuring. Keep in mind that virtually all cutting edge science is very indirect. We don't actually go to a black hole and put some kind of a device hanging out the window and measure the gravitational field. We don't go and fly a probe to a supernova and say, this will be cool when that thing blows up. We measure things that are indirectly. Same way, the bond angle on the two hydrogens connecting to the oxygen on a water molecule. We certainly don't have an instrument to measure that directly. And so there's questions about, did you see what you thought you saw? And scientists will say, if they're being nice and they respect you, I think you were fooled. I think you're mistaken. I don't think you measured that correctly. If scientists are going to be if scientists are going to be a little more nasty, if they think you're less than an honorable person, they might say, I think you're trying to fool me. Now, an example of these two things, excuse me, friends, Lamarck's theory of evolution, and the Soviet Union notoriously championed this in the early part of the 20th century. Lamarck said, if your dad has big, strong arms, his children will be born with big, strong arms because he worked to develop them. If you work to become an Olympic runner, your children will be born able to be Olympic runners because what you acquired as a physical change through effort can be transmitted directly to your children. This is not true, by the way. It's been disproven. And yet, people accuse Lamarck of being malicious. Probably not. He was fooled. He had an idea which was not correct. This happens all the time in science. People have ideas which are interesting and worth investigating, but it turns out at the end of the day, you weren't correct. You need to throw that hypothesis away. The cold fusion debacle. I don't know, Paul, if you're old enough to remember that. Some of our listeners probably are. Cold fusion was a flash in the pan giant news story, back about 1984 or thereabouts. The two scientists, Pons and Fleischmann, claimed to have found a way using palladium to force hydrogen through a filter, and the filter would actually squash the atoms together and cause them to fuse and produce helium and release energy. And had it worked, you could have had the Mr. Fusion tabletop reactor, infamous from the Back to the Future movies that's on the back of the DeLorean. You could have literally had a tabletop fusion reactor the size of, say, a modest ice maker or a big slow cooker. And this thing could be fed hydrogen and power all your household needs. I was working at Caltech at the time, and there was a big flurry in the physics department. Is this true? And they were trying to replicate the results. In fact, they found they could not replicate the results. And cold fusion became just one. And a lot of people said Pons and Fleischmann were scamming people. They didn't believe they were honorable. So again, when someone says, I don't think you measured that correctly, the first type of criticism says, I don't think you're very good at your job, bud. The other one says, I think you're unethical. I think you're a sinister figure in the scientific community. We talked about some of that with the research into the Alzheimer's stuff. And these people who were running this research and made lots of money off of it, they were promoting something which, in fact, no one's been able to replicate. The other way scientists attack is they say, I don't think you interpreted that result correctly. The idea that we measure something and people will agree, that's the measurement. That's the measurement that I see when I use my telescope, my spectroscope, my balance, right, for measuring mass. Yes, I see these things, but I don't think you're interpreting it correctly. Facts don't have any meaning in and of themselves. They simply are. The ground is hard, the sky is blue. Oh, but now you say, why is the sky blue? And why is the sky that color blue? And now you get into Rayleigh scattering and the size of nitrogen atoms and molecules and etc., etc. So, how do we interpret the facts that we see? Darwin came back from his trip around the world and his visit famously to the Galapagos Islands, and he said, I now believe I have seen evidence for natural selection. There were lots of people who said, no, Charles, you didn't interpret that correctly. Darwin's interpretation has stood the test of time and rigorous scientific debate. But we have to realize that there's a larger context in which we interpret the facts in the fabric of all scientific knowledge is disputable. Just recently, the Chinese rover that saw the rock that looked like a hut on the moon, the NASA rover on Mars, the doorway on Mars. And people said, it's a doorway. And the geologists at NASA, after looking at the photos for a while, said, no, this is a rock fracture. And then, no, it's rectangular. It must be a doorway. It's only about 18 inches high. So if it's a doorway for very small creatures, be about appropriate size for a corgi or a small house cat. So there's dispute all the time. This is not necessarily bad. And the fact that someone who is not a scientist disputes it is also not bad. But when someone disputes and then decides, I'm going to keep these facts, I'm going to reject these others, if we start parsing and deciding which part of the fabric of scientific knowledge I'm going to accept, then we wander down a bad road. When someone says, I don't think you interpreted that correctly, or I don't think you measured that correctly, this is the call for the scientific version of a duel. If it was the old West in America, we would have the scientists' gunfight. And the scientific duel, friends, is just an experiment. Consider something we've talked about often on this program, the idea of the geocentric and the heliocentric solar system concept. The geocentric system says the Earth is the center of the solar system, and the sun, the moon, and all the planets revolve around us. The heliocentric system says the sun is in the center, the Earth is but one planet of many, and they all orbit the sun. Only the moon orbits the Earth. These two theories coexisted for millennia. And the reason they coexisted for thousands of years is that no one had the technology or the cleverness to develop an experiment that says, if heliocentric is true, I should see this, and if geocentric is true, I should see that. I cannot see both things. We need an experiment to tell the difference. This is one way it's done, where someone says, I have an experiment which will give two different results depending on which idea is true. Much more often, as happened with the geocentric and heliocentric system, someone invents a new device, figures out a new technique to conduct an experiment. Galileo did both. He invented the astronomical telescope. No, it wasn't the first perspective glass, but it was the first truly astronomical telescope. And he observed the phases of Venus, and he reflected for a while, and he said, but wait a minute. If the heliocentric system were true, I should be seeing these things. And I'm not, and the things I saw are perfectly understandable in terms of the, I got mine reversed. If the heliocentric were true, I would be seeing case A. If the geocentric were true, I was seeing case B. And in fact, he realized that his results with Venus changing in size as it goes through its phases only works if Venus is a planet orbiting the sun, not if the Earth is in the center and Venus and the sun both orbit it. So that's where we are with facts. Okay, if that's a fact, what is an hypothesis? Let's not hear the tired, A hypothesis is an educated guess. No, no, no. Not only is that bad grammar, it's just not true. Scientists don't make their living or become well known by being good guessers. No. An hypothesis is a proposed explanation for a limited set of facts and observations. Oh, look, I go to the desert and I'm looking out in the desert in Utah or in Arizona, and I see these peaks where I see rock built up in layers, and I go chop out some of the rock from some of these layers, and I realize that I can take this rock and I can pound it and I can knock it back down into the individual sand particles, and I come up with an hypothesis which says, gee, all of these things must have been sometime actually been sand at one point, and some sort of geochemical process cemented them together. Perhaps they were sands that settled to the bottom of a lake. The pressure from the water and the chemical reaction of the water and biological materials cemented these together as sandstones. Well, we can have a hypothesis, but they're limited. Hypotheses talk about, oh, this explains this small corner of everything we know. Now, we can have a broad hypothesis which proposes something may be true. We talked a couple of episodes about the anthropic cosmological principle, or the weak anthropic principle, and this is a conjecture. It may be true. Mathematics is full of these conjecture sort of things. One of the famous ones is the Collatz conjecture, which has to do with how you can set up a rule, and with any number, does it always come back to one? Fermat's last theorem, a squared plus b squared plus c squared, can you raise it to any arbitrarily high exponent, and will it still be true? And these sorts of things are conjectures, and if they're mathematical, people sometimes can prove that they are true or prove that they are false. But if it is a scientific conjecture, and you could say, all of evolution is driven by the idea of survival, or the mechanism of survival of the fittest, this is a conjecture. Proving this in the case of a scientific conjecture is very, very difficult. A focus hypothesis deals with narrower scientific explanations for known physical processes or facts. And if we look at conjecture, human beings could manage to come up with a way to travel between the stars, interstellar travel. That's a conjecture. We don't have the technology now. Could we do it? I don't know. Focused hypotheses, we talk about the famous debates between Kip Thorne and Stephen Hawking. Will black holes be discovered and accepted as existing by the scientific community? They used to make bets, and they used to bet magazine subscriptions on whether or not these things, and some of these things ran for decades. The focus hypothesis of the geocentric and heliocentric solar system. When Aristotle and Copernicus were talking about it, they were talking about our solar system. Later, the Copernican principle said, this applies everywhere. So we've got the geocentric and the heliocentric hypothesis and all of these things. Unlike facts, which are just found in nature, an hypothesis is a creation of human beings. It's not found in nature. Instead, an hypothesis seeks to explain nature. An hypothesis seeks to explain nature, explain what we know, explain what we found, explain a connection of facts and their relationship with each other. So we say things like, we have two competing hypotheses. The only way we decide between them is with an experiment. The idea is simple. Although an hypothesis is a human creation, we invent them, we write them down, we discuss them, we share them. But when we do an experiment, nature decides. When we do an experiment, the idea is that if the experiment is honest and it's not rigged and we control all our variables, then nature informs us what's true and what is not. The outcome may be indeterminate. When we do an experiment, we don't always get a clear answer. And sometimes we have an outcome which can be accounted for with many different hypotheses. I'll give you a couple of examples from relatively recent time. The Martian meteorite, Allen Hill's meteorite. And this was tested, and a group of scientists looked at the electron micrographs of the interior. And one group of scientists, look at these chains of bubble-like structures. They must be microfossils. These are fossilized remains of ancient life on Mars that were fossilized billions of years ago, and that piece of rock was kicked off of Mars by a huge impact or volcanic explosion. It was launched into orbit. It drifted around the solar system for millions of years. It came down as a meteorite. It landed in Antarctica on the Allen Hills Plain, and it was discovered 10,000 years later. And this indicates Martian life. Other people said, oh no, those aren't microfossils. Those are simply microgeological crystallizations. And these are created by geological processes. Some of the things in the Martian meteorite, the magnetic crystals. On Earth, the only way to produce those sorts of crystals, they're produced biologically. Animals, small microscopic creatures line up with the Earth's magnetic field and produce these crystals of magnetic material through biological processes. Some of the other scientists said, no, we're sure they're geologic processes. However, we just can't reproduce it yet. So sometimes things are indeterminate. The whole process of trying to discover water on Mars, trying to discover life on Mars, we have a lot of outcomes, and part of the problem is the closest we get is 75 or 80 million kilometers, 50 million miles, and that's the closest we get. And we say, well, we're getting this data from rovers and we're not there. We can't actually look at the rocks. And so sometimes people just say, I'm not satisfied. To an extent, that's a legitimate thing to say, providing you say, I'm not satisfied because I have an alternative explanation. Number 2. Number 3, I think your hypothesis is flawed because. Number 4, I think you're interpreting your measurements wrong because. When you get some troll on the internet who says something like, nobody's really proved we landed people on the moon in 1969, that's just someone who's just saying, can't see the evidence. You can't prove it to me. There's none so blind as those who will not see. Isn't that the old quote? I think that's pre-biblical, but that rings true today, 2022. And so we realize sometimes the outcomes, though, are quite magnificently clear and obvious, because sometimes we get an outcome where we say, if the other hypothesis were true, this couldn't possibly happen. If the other hypothesis were true, this result would be impossible. An example of that, the Michelson-Morley experiment. Back in the 19th and early 20th century, the idea, which had been prevailing for hundreds of years, is that light traveled through not a vacuum, but space was filled with this very rigid, very thin material called the ether. AETHER, not the kind that they knock people out with in operating rooms. This is the ether, and it's this interstellar medium, and it is the medium through which light waves wave. And Michelson and Morley said, well, if the ether is out there, and the Earth orbits the sun, and the Earth rotates on its axis, you would think that at some point, dawn, you would be traveling forward in the same direction in which the Earth is moving around the sun. And so you would have a high relative velocity to the ether. And at the other hand, if you did this experiment at sunset, you're rotating away. And the rotation of the Earth is carrying you in opposite direction from what the Earth is moving through space around the sun. And so if you did it at noon and shining straight up, you should get no deviation at all. This is kind of like a Doppler shift idea, right? Are the waves coming towards you, going away from you, or are you looking at them going transverse across? And so you can't measure any Doppler shift. Well, Michelson and Morley, trying to measure the change in the speed of light using an interferometer, which gave you the speed of light to a tremendous accuracy, they were expecting to see some kind of change. No matter how they oriented the experiment, no matter which way they did it, no matter what time of day they did it, no matter what time of year they did it, they never found any deviation. Light seemed to travel at the same speed in a vacuum in any direction, at any time, at any point around the sun. It wasn't being influenced by a medium at all. And if that's true, well, how can the medium possibly exist? And so many people were distressed by this outcome. Oh my God, this upsets all of physics. And in fact, it kind of shook up the can pretty good. But their result held sway, and people looked at it and became convinced. And there were other experiments, and people repeated it. And they said, wow, it must be true. The ether, which people have believed in for hundreds of years, since the time of Newton and before, just doesn't exist. And so the ether hypothesis was disproved. It's false. It doesn't exist. Sometimes it turns out the technology we need to perform a specific experiment doesn't exist yet. This was the case with the heliocentric and the geocentric system. We have Aristotle on one side, Copernicus on the other. And they weren't the only two advocates of those two theories. I just cite them as examples. But great debate in the scientific community post-Copernicus. Is Copernicus right? Is Aristotle right? And a lot of people were and said, bah, humbug, to this Polish monk and all his crazy observations. And other people said, no, Aristotle, bah humbug on him. He's old. He lived thousands of years ago. How could he possibly know? Well, we look at that and we say, gee, how can we possibly, and people fought about this literally for centuries, and there was no answer except I believe case A, I believe case B, and people died for this. Galileo went to prison for the rest of his life for this. Giordano Bruno was burned at the stake for this. Copernicus himself was so terrified of the Inquisition arm of his own church that he literally waited until he was on his deathbed to allow his manuscript to be published and released to the public. He had one student in all his lifetime. This brilliant man with this brilliant theory took only one student under his wing. So competing hypotheses sometimes exist in a state of tension. The Higgs boson. The Higgs boson exists and explains why everything has mass. The Higgs particle does not exist. And we still don't understand why particles have mass. And this went on. Higgs proposed this in 1963 or 4, and it was the synthesis of work that's been going on for a couple of decades. And it was decades later, after CERN was built, and they did the experiment and they said, aha, I think it was 2012, we've discovered the Higgs boson. That discovery paper, where they released it to the world and said, here's our paper describing how we built the collider and what we did, and here's the results, and here's how we interpret them, and here's why we think there's actually a Higgs boson. That paper had 1,600 authors. Can you imagine going to work on a committee with 1,600 collaborators? I cannot. But you have to realize, we see scientifically ignorant people in politics, in the news, in the media, on social media, literally all the time, every single day. And you see them at the heads of government. Well, our government says that 97% of scientists agree that man-made global warming is a real phenomenon and an existential crisis. Hello, do you realize that in Copernicus's day, literally everyone else on the planet thought the old Polish guy was wrong? Science isn't about poles. We had trials in the United States. 1925, the Scopes monkey trial. A teacher, was put on trial for teaching Darwin's theory of evolution. Science is not about poles. The fact that 96% of scientists agree, this is like 4 out of 5 dentists agree on the best toothpaste for you. It means nothing. It means it has zero scientific validity. And when you see someone citing that as evidence to support a theory, you know they are a scientific ignoramus. They don't understand science as a process or a culture at all. Science isn't about poles. Okay, facts, hypotheses. What about theories? A scientific theory is a sweeping explanation for a broad set of facts and scientific observations, and it explains how all of these facts are interrelated as well as how they interact with each other. Okay? Wegener, who is a German geologist, looked at the maps of the Earth and said, why does it look like South America should fit right up against Africa? And why do I find fossils on different continents that are obviously the same age and of the same group of flora and fauna, when all of this stuff, the mid-oceanic trench and earthquakes and continental drift, and Wegener came up with the idea of continental drift. He said, no, the continents are not stationary. And this explains things in archaeology, it explains things in paleontology, it explains facts in geology, it explains facts about earthquakes and volcanism. And Wegener had this idea. He died before enough evidence was brought forward to say, yes, we as a scientific community accept this theory now. But he said, this idea explains all kinds of data across lots of different fields. Alvarez and Alvarez, father and son, 1980, not that long ago. They said, oh, we found this iridium layer and it's global. And we think there was an asteroid. It would have been a hella big asteroid. And it whomped the Earth and it created a nuclear winter, if you will. And the lack of sunlight and the cold and the collapse of ecosystems destroyed the dinosaurs. This is why we have the KT boundary. And this is why we have geologically dinosaurs up to this point and then not at all after that. They said this explains a whole lot of facts, paleontological, geological, globally, worldwide. Wow, big knocked the hell out of ecosystems. And that took until the early 2000s to be really broadly accepted. So we have these ideas that a theory seeks to explain everything we know about a well-defined area in nature. So we talk about a scientific theory. Goodness, this is often the life's work of a scientist or sometimes a large group. Hubble's theory of the expansion of the universe. He had these ideas. Georges Lemaitre had these ideas, and Hubble went and he got appointed to this observatory, and he's got the world's biggest telescope now and new camera technology that he and his colleagues help invent and develop. And he looks and he finds redshifts in galaxies. And he says the whole universe is expanding. By the way, his data set, about 25 galaxies. We think there are hundreds of trillions. He found 25 and he said, game over. That's a lot of brass, folks. That's just confidence in your data set. Even Einstein was saying, I'm sorry, you're wrong. And Einstein was wrong. Everybody was wrong. Hubble was right. Relativity theory, the work of a single human being, a single man, Albert Einstein. And it took him more than a decade between the special theory and the general theory. And he'd been thinking about it for many decades by the time the general theory came out in 1915. The Higgs Boson, as we said, the original idea was one man, but by the time it was proved, a cast of thousands, like a Cecil B. DeMille movie. So why are we wrong when we say, you can't prove that theory? Why is that scientifically ignorant, a faux pas of the first water? Well, it turns out that we cannot prove a theory, not in the mathematical sense of proof as most people and most scientists understand it. We can say 2 plus 3 equals 5, and we can mathematically prove this. The idea of the Pythagorean triangle, a squared plus b squared plus c squared, gives us the ratio of sides, and we can mathematically prove this. We can prove that it's true for all time and all triangles everywhere. Theories about nature are not so tractable, mostly because things in nature are not so universal and precise and unchanging as mathematics. We take a look at mathematics as we take a look at addition or prime numbers or the digits on the number pi. And we say, okay, well, we look at these mathematical facts and they are the same regardless of culture, language, era, location. 3 plus 2 equals 5 is universally true. The Pythagorean proof of the triangle is universally true. And we can show that it's true for all time because the idea of two-ness or five-ness or squaring never changes. Nature is not quite that tidy. We can have groups of scientists, and they can agree on methods of observation and measurement. Oh, we're going to use this kind of a spectroscope. We're going to use a telescope with a mirror of this precision. We're going to put this sort of an infrared or visible light sensor in a camera. And we can agree on methods of observation and measurement. We can do that. And because we can agree on methodologies, this means that other scientists can come along. Number one, they can repeat our experiment. They can repeat it exactly. They can get the same equipment from the same source. They can set it up under the same laboratory conditions, and they can run it again. And if the experiment is valid, they should get the same results every time. Now, are they going to interpret them the same way? No, interpretation is a human thing. That goes on in your brain, not on the laboratory table. Uh, the replication of results gives the scientific community confidence that the fact of the measurement is true. I measure this Rockwell hardness of this stone that I found, and it is X, and I give you the number, and I say, okay, you can measure it too. And we can, maybe there's, oh, well, I used a particular kind of limestone. I used a different technique. It allows people to look at your experiment and say, I can refine that. I can make it more accurate, more precise, more reliable. We could measure that in a different way. You know what? If you measure something in two different ways, you should get the same answer. If I measure the distance between my eyes and I use an American tape measure, and I go, how narrowly set are Dr. Barth's eyes? And I use a meter stick, and I go ahead, or I use a laser, or somebody says, oh, use a giant pair of calipers. Well, you know what? Sorry? 8 minutes. We got it. We're gonna wrap this up. Basically, this allows replication of results, allows people to have confidence in the fact, and we use these facts that we have confidence in to propose a hypothesis. We can disprove a hypothesis by saying, oh, it predicted this and it came out that. Aristotle said, oh, one side of the moon's dark, the other side is bright. In that case, if you try this with a coin, one side painted dark, the other side bright and shiny, you cannot in any way hold the coin to come up with phases. The experiment disproves the hypothesis, but theories are universal in nature. They go to the heart of the matter. They describe phenomena of nature and how nature works, things like gravitation, autobiogenesis, the Big Bang, universal inflation, the expansion of the universe, the quantum nature of reality. But if we're going to prove a theory about relativity or the quantum nature of reality or any other thing, we have to, if we're talking about proving in nature, then it has to be universal. It has to be ubiquitous in time, always true. Ubiquitous in space, everywhere true. Ubiquitous in every particular. And you know what? We can't collect that set of data. It's physically impossible for us to do so. So a theory can never be proven true, never. But you can always prove it false. If you find one planet where things fall up, then this disproves the idea of universal gravitation. And when you hear people in the mob howling, that's not a fact, it's just a theory, or you can't prove that, it's just a theory. These are the loudest, proudest declarations of scientific ignorance you will ever hear in a public venue. Some people treat them with contempt, other people treat them with compassion. But in any case, friends, when someone howls, you can't prove that, it's not a fact, it's just a theory, as if theory was short. My son, who is an engineer, says we call those a WAG, wild ass guess. No, theories are not wild guesses. We do not treat these howlings of the mob with the same respect due to scientific arguments. And I don't care if it comes out of the mouth of some troll on the internet or if it's a government minister saying 96% of scientists agree. Sorry, that's not scientifically valid, and no one should accept it as proof or demonstration of anything. What we need to do is we need to have better education. That's what I do. Try to train teachers to teach students. I've had about 7,000 students in my career come through my classroom. The students that I've had in the last 9 years at my university will teach more than 500,000 young people if they have a long, successful career. So we can't prove when a troll says, you can't prove the Big Bang, it's just a theory. We can try to educate them, but we shouldn't treat them as equal players on the field of scientific thought, debate, discussion, and experiment. That's where we're going to wrap up. By golly, we're within our time limit. And Paul, did we have any fun questions for today that we can answer in the last couple of minutes? Why does the Webb telescope have 18 mirrors instead of 2? The mirrors are essentially segments. If you could make something as big as Webb and put it into one piece, that would be technologically an amazing challenge, and we don't have any launch vehicle that could put it in space. By making segments, we reduce the manufacturing challenge to something we can handle, and this thing folds up so we could put it inside. I believe it was launched in an Ariane rocket, and it actually unfolded the 350 or so steps that made it unfold into a working telescope. Science culture, what does it mean? Science culture is a set of rules and understandings about the nature of fact, hypothesis, theory, the nature of repeatability of experiments, and the way we treat ideas. Realize that science isn't a steady march of culture, but a steady work of science will always disprove a false idea. A false theory will always be disproven given enough time. Sometimes it takes centuries. The progress has really speeded up recently, but false ideas may hang around for a long time until we invent the technology to do the right experiment, but they will not last. True theories are eternal. They will be modified, they will be changed as they develop, as we get new evidence, but false ideas will always die and crumble. This is the idea of what Karl Popper said, science as a culture is about falsifying the bad ideas. That's why scientists engage in this vigorous and sometimes vitriolic debate and conflict about what's true or which interpretation is valid. So there we go. We have time for maybe one more. Do we have one more? Maybe not. When this happens, sorry? Okay. Mathematics and science through years of knowledge stuffed into the James Webb telescope, which basically makes it a time machine. And yes, indeed. The farther out we look in space, the farther back we look in time. Not only that, but the Webb telescope, just like the Hubble, just like Newton's first reflector, is a time capsule of the state of the art of science and technology on the day they were built and put into service. We think of the great Palomar telescope. It's a time capsule from almost a century ago of what was the state of the art on that day. And that in itself is historically interesting as well as scientifically interesting. So there we go. Let's talk about next week. We are going to talk about Einstein and his famous theory of relativity. He hated the name, by the way. And we're going to talk about how Einstein has been tested over the years in some of the latest tests. And why do we keep doing these tests? And how do we interpret the result? It turns out every time somebody has said, aha, I think Einstein's wrong, that evidence has been proven false or inaccurate or badly interpreted. Einstein's theories have stood the test of probably the most rigorous set of scientific tests of any theory. And it's been going on for 115 years, and we don't think it's going to stop anytime soon. We keep developing new technology, and we keep on testing it more and more accurately. So we'll talk about that next week. And our mass and what else describes a black hole. Mass, spin, electric charge, and magnetic field. And that's about it. I hope folks you'll go out and get a copy of Star Mentor if you have not already. If you're interested in astronomy education, download the free book, Astronomy for Educators. And please, if you've had a chance to look at the book, leave us a review, because those are really important and help other people find these important resources. By the same token, please share with your friends your passion for How Do You Know. Come back next week and see us again. We're going to have an exciting program. And again, if you have questions, you're welcome to email me, astronomyforeducators@gmail.com. You're also most welcome to send us ideas for programs. Doc, I'd like to see you do a program about this topic or that topic. We'd love to hear from you. And we want to thank you for joining us again this week on How Do You Know?